So in this part, we're going to introduce an idea of what absolutely needs to happen for a series to possibly have a chance to converge. And again, I want to emphasize this idea of possibly. What we're going to talk about now is not enough to guarantee that a series converges, but this just needs to happen for a series to possibly converge. Okay. And we're going to build up this idea slowly. So for example, say we have the following kind of goofy series. We have little n from 1 to infinity, and our series that we're actually considering is just the number 1. And again, since this is an infinite series, what we're actually doing is we're adding together an infinite amount of ones forever. Okay. Now, hopefully your gut instinct on this is saying, well, if I'm adding an infinite amount of ones, I have 1 plus 1 plus 1 plus 1 plus 1 forever. And as we just keep adding ones together, there's no way that this series is going to be anything but divergent or anything less than infinity if we're literally going to be adding ones together for all time. So let's talk about another series. This series is of a similar flavor, but instead of 1, let's talk about adding together the following number, 0.01. Okay. And again, what this series actually represents is the infinite sum of 0.01 plus 0.01 plus 0.01 plus 0.01 forever and ever. Now, if we're adding together 0.01 plus 0.01 plus 0.01, if we're adding this forever and ever, you know what? Eventually, this number or this sum is going to be huge. Say we're adding together 0.01 plus 0.01 for the rest of the day, for the rest of the week, for the rest of the year. This number is eventually going to get greater and greater and greater. And you know what? It's actually going to come out to infinity as well. It's just going to get out to infinity a little slower than the first case, where all we're doing was adding ones, while in this case, we're adding 0.01. Well, this same idea is actually going to hold if we do other series of a similar nature. Say instead of 0.01, forever and ever now, what we're actually going to add is 10 to the minus, 20. So what this series is, again, every single addend in this sum doesn't depend on the indexing variable n, but is instead just 10 to the minus 20 plus 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 10 to the minus 20, and so on forever. Now, if we really wanted to waste a lot of time, we could just keep adding 10 to the minus 20 plus 10 to the minus 20 plus 10 to the minus 20. And if for whatever reason we had 1 billion years ahead of us just to do this, eventually this number is going to start getting astronomically large. So even though it's much smaller than 1, it's much smaller than 0.01, eventually when we add 10 to the minus 20, that's point with 20 zeros and then a 1, this number is going to add up to infinity as well. So, what we're basically seeing at this point, if we have a non-zero number, and we just add that non-zero number to itself an infinite amount of times, we are guaranteed that that series must diverge. Let's think about this in relation to a more general series now. So, thinking about a more general series, if we have say a general series n equals 1 to infinity, just say of a sub n, as general as we can get, and we're adding together a1 plus a2 plus a3 and so on, and we're getting to some very, very large numbers down the line, say a 1 million or so, and plus other numbers. Now, if we want this sum to converge, what we're going to hope is some of these numbers down the line, like this millionth term, or maybe the billionth term, the trillionth term, the gigaplex term, we're hoping that eventually these numbers that are way, way far down in this sum, we're hoping that those numbers start getting smaller and smaller. Now, what we saw previously with an example like the goofy example of just adding 1 forever, those numbers down the sum, they're still 1. These numbers aren't getting any smaller. So we're just adding the same thing to itself. We even saw this in the case of 10 to the minus 20. If all these numbers were 10 to the minus 20s, it's going to be real messy. Even if all these numbers were 10 to the minus 20, the fact that really, really far down that sum, those numbers are still a non-zero number, and we just keep adding non-zero numbers to itself, those numbers eventually get larger and larger. So what we actually need to happen in order for the series to have a chance to converge, these numbers really, really far down the list, like the millionth number, or numbers, say, the billionth number, and so on, we need these numbers to look very, very close to 0. Or they start looking very much like 0 in a limit. So let's write down our thoughts. So for a series to have a chance to converge, the terms really, really far down in the series all need to start looking like 0. Now, this sounds somewhat familiar from when we talked about sequences. For sequences to converge, we were asking the question, hey, you know what? What do those numbers really, really far down in this sequence, or really, really far down in the list, what do they look like? If they all look identical, then we said the sequence was convergent. In this case, what we're saying, for a series to have a chance to converge, again, I want to emphasize to have a chance to converge, when we need all these terms to look like actually are 0. So all the terms really, really far down in that infinite sum, those terms that we're adding very, very far out in the sum, they all need to look like 0 in order to have a chance to converge. Again, we're not guaranteeing convergence, we're just saying to have the possibility to converge. So what this actually reminds us of, if we're starting to investigate terms really far out, we're going to introduce a limit. So let's do that now. So basically what we're saying is, if we have an infinite sum, say the sum from n equals 1 to infinity of a sub n, for this sum to have a chance to converge, we need the following to happen. We need the limit, as we explore the terms really far down in the series, by taking the limit as n goes to infinity of our series generating function, a sub n. We need these terms to look exactly like 0. If these terms are anything but 0, we get to automatically say that that series has to diverge. We need this to happen just to have a chance of convergence. So let's do a few examples of that now. Okay, So let's do a couple examples of seeing if we can see when a series converges or diverges based off this test. So the first example, let's consider the series from n equals 1 to infinity of, say, n squared plus 1 all over 3n squared plus 7 or minus 7n. Now, what we just said was we want to explore the terms really far down in this series. So let's take a limit as n goes to infinity of our series generating function to do just that. So we take a limit of n squared plus 1 over 3n squared minus 7n. And if we take this limit as n goes to infinity, what we see in the numerator is n squared plus 1 goes to infinity. In the denominator, we see something similar. So we get to do our friend L'Hopital's in this limit. So doing L'Hopital's, take the limit, the derivative of the numerator and denominator separately. So the derivative of the numerator is just 2n. Derivative of the denominator is a 6n minus 7. And oops, lo and behold, we see the same thing happen, so we get to do L'Hopital's again. Which in this case, the derivative of the numerator is just 2, derivative denominator is 6, and we see that this comes out to 1 over 3 or 2 over 6. Now, what we get to say is those terms really far out in the series, they all start looking like 1/3. So maybe like the billionth term or the trillionth term. These are looking very close to 1/3. So forever after that point, we're starting to look like we have the sum is 1/3 plus 1/3 plus 1/3 plus 1/3. So from the arguments we made before, that series has no choice but to diverge. So this series is automatically divergent. Let's do a couple more examples now. So example 2. This is the series from n equals 1 to infinity of 1 over n. We're going to get to know this particular series in a little bit. This is called the harmonic series. But let's see what happens if we apply our test for divergence on this harmonic series, where we take the limit and ask what do the terms really far down in the series or this infinite sum begin to look like. So we take the limit here as n goes to infinity of 1 over n. If we take the limit as n goes to infinity, that numerator is finite, but that denominator is growing very, very quickly towards infinity, and this thing looks like 0. So let's talk about this for a moment. The limit is equal to 0. So at this point, this series, all we get to say is that it has a chance to converge but it could still diverge. So again, this test that we're doing with the limit, even though it passes this test, we got a 0 limit here. All this says is this series has a chance to converge, but it still could also diverge. It's basically like saying, you know what, it just passed the first test of many. And just as a nice spoiler, this harmonic series, we're going to show in a little bit that this actually diverges. So even though it passes this first test, this series ultimately actually is divergent. Let's do another example. So this is an example of the following series. The series from n equals 1 to infinity of 1 over n times n plus 1. So again, to use this one test we have so far, we're just going to take the limit as n goes to infinity, and what this does for us is we are exploring those terms really far out in the series. And when we take this limit, that numerator again, it's finite, but that denominator is growing towards infinity. So again, in this case, this limit is 0. So at this point, what do we get to say? All we can say is it might converge, but also still could diverge. So this series test, what you could actually think of it is like a sieve, in which case we feed a bunch of series into this series test. Only a few series get past this series test. But even if it gets past this series test, it still doesn't automatically mean it converges. On that note, it still doesn't automatically mean it diverges. It just passes the first test. In the next couple weeks, we're going to go over different tests in which we can try to figure out if series converge or diverge if they pass this particular test. So let's sum up what we know so far. The first thing, in order for a series to converge, if we have a general series, say n equals 1 to infinity, of a sub n, in order for this series to have a chance to converge, we need the limit of a sub n to equal 0 as n goes to infinity. Again, I want to emphasize, this is just saying to just have a chance to converge, we need this to be true. The second thing we get to say, though, is, you know what? If we do take the limit of a sub n as n goes to infinity, and this doesn't equal 0, the series is automatically divergent. In this particular limit test here, this is what we call the test for divergence. And the way I like to think about it for series, is the test for divergence is analogous to like our U substitution for integration. When we first see an integral, we ask ourselves, hey, could we just do this with a U sub before we start introducing the higher level machinery like integration by parts, trig sub, partial fractions, etc. So the test for divergence, when we're given a series and asked, hey, does this converge or diverge, it should be the first thing we do. Again, because it eliminates a lot of series that are divergent just because the limit doesn't equal 0. But if the limit does equal 0, again, it is no guarantee. All this says is it has a chance to converge. Again, it still might diverge. So let's go over two more series, the harmonic series, and we're going to also explore another series called the telescoping.